Hey y'all, I miss you. So today we're uh, going into day 2 of Taylor polynomials and Taylor series. Taylor polynomials were, oh, that's funny. Um, Taylor polynomials were named after Brooke Taylor, an English mathematician. Um, Unlike Newton, he did not invent calculus during the plague. But Colin Maclaurin also invented a particular kind of Taylor series. That particular kind of Taylor series is centered at 0. Although that was written about in the notes from Monday, I felt like I should re-emphasize that because that is a very important distinction, and your professors are going to expect you to understand that a Maclaurin series is just a Taylor polynomial centered at 0. So, to use Taylor polynomials effectively, we need to be able to estimate the size of the error. And that error is provided by Taylor's theorem. Okay, so I think, let me check just a minute, because I think I need to go to the next screen to explain this. Okay, so I don't go to the next screen to explain this, but, I usually wait until later. It looks like a bunch of gibberish, doesn't it? But I think if you let yourself kind of relax your brain, this right here is the remainder, and that remainder is defined as follows. Now, I remember one year I got some really, really good questions on this, and that was actually almost exactly 5 years ago. Class of... I'm going to have to look it up because I think I'm misremembering. Anyway, I will explain all of this later. Hopefully I'll remember to explain it. If I don't remember to explain it, please let me know, because right now it looks like gibberish though, right? So Taylor's theorem tells you that this remainder is, actually I'm going to explain it right now, is defined as sums. Okay, so this Taylor series in front of you, and let me see if I can work with this a little bit. This Taylor series in front of you has a remainder, and that remainder is defined, the Taylor series is centered at C. That remainder is defined as some value between x and c, some value of y, where z is a number between x and c, and this is the next term. I feel like that wasn't very well explained, but I will try to go into it later. Sorry, guys. Okay, so all I was trying to say is that all we know for sure is there is some value between x and c that is equivalent to the remainder, and that particular value gives us a bound for the error, but it doesn't give us the exact value of the error. That is an important distinction. This is called the Lagrange error bound, or Lagrange's form of the remainder. We'll study that more later, but I've tried to put it in super general terms because you're not ready for the whole kit and caboodle. Okay, so just know that there's some sort of upper bound that can easily be defined, and that upper bound is going to be greater than or equal to the remainder, and you won't be able to find the exact error. Okay, here is where all that work we did with the graphs of f prime, and f double prime becomes more obvious what their usefulness is, because you're going to need to understand certain things about the derivatives and how that affects the graph and how that relates to your Taylor series going forward. So if we look at this simple graph for which we have no numbers whatsoever, we can actually figure out the signs of A, B, and C. So A is necessarily your y-intercept, because when x is 0, B and C, poof, go away. I mean, they don't really go away, but you know what I mean. So A has to be positive because A is your y-intercept. B also has to be positive because that is the slope of your function. The entire time, that whole entire slope is positive. So f prime of 0, and then we get to our second derivative, and we see when we take the second derivative that is concave down, or our second derivative is negative. So that right there should seem pretty straightforward to you. And if you do not understand the graphs of f prime, and f double prime, and how they all interrelate, and you want to review that, please let me know, because that is usually a fairly heavily tested item. Okay, here we go. Suppose that the function f of x is approximated near x equals 4 by a third degree polynomial such that p sub 3 of x equals 2 minus x minus 4 squared plus 8 times x minus 4 cubed. Notice that the degree is 3, so we could call this a third degree Taylor polynomial, or we could call this a Taylor polynomial of 3 terms. We could call it a Taylor polynomial of 3 terms because we have 1, 2, 3 terms here. Understood? Okay. Most of the time, those things aren't going to match. A Taylor polynomial of third degree might have 4 terms, because if you look here, we do not have a linear term. So we're going to use this information to find f of 4, f prime of 4, the second derivative at 4, and the third derivative at 4. Okay, when you look at f of 4, you should just have 2 because the second 2 pieces zero out. When you take the first derivative, everything zeroes out. At the second derivative, you should get negative 10. Double check and make sure you understand how I got that. And the third derivative at 4 is going to be 48. Again, double check my math. I actually know I did it right for a change, but double check and see if you can follow along there. Does f have a local maximum, minimum, or neither at x equals 4? Well, we know that the first derivative at 4, sorry, having a few issues here. The first derivative at 4 is actually just 0. And we know that the second derivative is negative. So if that is true, we have something that is concave down. Sorry, my cat just stuck her toe in my face. Second derivative is negative, and the first derivative is 0, so whoop, we have something that looks like that. So it has to be a maximum by the second derivative test. Okay, moving right along. The function has derivatives of all orders for all real numbers, x. Oops, this is the wrong slide. Where'd my other slide go? I'm going to have to fix that. Bye. Oopsies, my brain was on the wrong slide. Okay, so here we go. The function f has derivatives of all orders for all real numbers x. Assume that f of 3 equals negative 4, f prime of 3 equals 2, f double prime of 3 equals 7, and f triple prime of 3 equals negative 5. So use that same formula that we used yesterday to, or not yesterday, Monday, to find the formula using that whole Taylor polynomial series thing. And we're going to go ahead and do that. We're going to have our Taylor polynomial right in front of us. And then we're going to do something to tweak it, which is something they expect you to be able to do very quickly on the AP exam. Okay, so some tricks to remember the formula here. This first, I feel like I need to underline what I'm talking about. This first bit right here, oh, that's a weird underline, will always involve no x values. Then you've got your first derivative. Oh, this is doing weird things. Your first derivative and the exponent of your x minus 3 is 1. Your exponent in that first bit right here, the exponent was 0. And then this is actually, you could think of this one right here. Well, this is just behaving. This is a weird tool. That one right there, you can think of it as the first derivative, the first power, all over 1 factorial. The third thing, I'm going to use something different here. I mean, not a different tool because I'm kind of entertained. Okay, so your second derivative, your second power, and 2 factorial. The last one, third derivative, third power, 3 factorial. Okay, so that pattern is pretty easy to remember. Hopefully through the homework you were able to figure that out. Now we're going to find the 4th degree polynomial. And instead of f of x here, they have f of x squared plus 3. Now what that does is tweak your entire formula. Instead of writing x, you're going to write x squared plus 3. And this is actually a Maclaurin series because it's all about x equals 0. So, noting all of that, we're going to go ahead and get to work. So, even though Taylor polynomials look absurd, once you get the patterns down, it's fine, right? I mean, I hope. I don't know what the correct verbiage is there. Now, what I do want you to notice, instead of writing x, we wrote x squared plus 3. Instead of writing x, we wrote x squared plus 3, yada yada. And then it simplifies into the next step where you just end up with a pretty little polynomial that's fairly simple. Okay, so when we simplify that and actually remember our exponents, which I did not, so I've circled them in red, big bold red. There should have been a squared up, I'm going to use that weird tool again. Up here, and there should have been a cubed here. Right here. There we go. Okay, so what happens now is when we simplify that out, we discover that we actually have not a 4th degree polynomial, but a 6th degree polynomial. And the problem actually just wants, or the question writer just wants a 4th degree polynomial, which allows us to eliminate this term. And our actual answer is right there. Capiche? Okie dokie. Onwards and upwards. Okay, an infinite power series, such as what is in front of you, is called a series of constants. Each term of the series is in fact a constant. An infinite series, such as what is written in front of you, is called a power series centered at x equals 5. Each term of the series contains a power of x equals 5. By definition, a power series is as written in this box. I'm just not going to read all that to you. I'm sorry. I have to assume you can read. I think it's really rude when people read the PowerPoints to me. So let's see, what pieces do we need to talk about? Every single power series converges at its center C, and power series have a certain sort of radius. So for power series centered at C, there are 3 possibilities. The power series only converges at its center. It converges within a certain radius, but diverges outside of that radius. And the third thing that is possible is that it converges for all real numbers. The number r is the radius of convergence of a power series. If the series converges only at C, the radius of convergence is r equals 0. If the series converges for all x, the radius of convergence is r equals infinity. The set of all values x for which the power series converges is the interval of convergence of the power series. The ratio test is used to find the radius and the interval of convergence. The ratio test says that a series will converge if the limit as n approaches infinity of the next term divided by the current term is less than 1. So we're going to find that limit and determine the values of x for which the limit is less than 1. So here we go. Find the radius of convergence and the interval of convergence. There are 2 different things. Oftentimes when we are grading these, we see that people only find the radius of convergence without finding the interval of convergence, or they find the interval of convergence without clearly stating the radius of convergence. So make sure you do both, even if you're in college. Every time you are asked to find the interval of convergence, you must check to see if the endpoints are included in the interval. Okay, here is what the next term divided by the current term looks like for this problem. We're going to simplify it. Once we simplify it, we're going to try to figure out the radius of convergence, then the interval of convergence. Okay, so what I want you to think about here is what confuses you here. I can tell you what confuses you. Okay, so let's see. I'm sorry, I'm having trouble putting my thoughts together. Okay, I feel like the quack right now. Okay, so when we go from here to here, the part that confuses people the most every single year is that I pulled this out front away from all of this. But if you really let yourself think about it, this first part has almost nothing to do with that. Actually, it has nothing to do with that limit. And we're trying to figure out the limit. Well, the limit there for that second part is just 1, which makes everything, when we take the limit, turn into the absolute value of x minus 5 over 2. Now we know that we want a radius of convergence. We know that we want the radius of convergence to be, let's see if I can put my thoughts together. The ratio test that says that a series will converge if the limit of the next term divided by the current term is less than 1. I am referring to this oh, that was weird. I don't know if you can see that. This right here. That's what I'm referring to. So we're going to go ahead and take this bit right here, and we're going to set it less than 1, and we're going to try to figure out for what values of x that must be true. Okay, so we know we have a radius of 2, and once we figured out that radius, we can figure out our endpoints. Now the tricky part comes in trying to figure out whether or not these less thans are strictly less than, or if they are less than or equal to. What we need to do is we need to examine the series at each endpoint. Okay, what we see here is when we plug this in, we're actually replacing x over here with 7. So 7 minus 5 to the n plus 1. I'm sorry, to the n. I boxed the wrong thing. 7 minus 5 to the n will just give us 2 to the n. And then we simplify that out and we see that these two cancel. And what do we have there? We have an alternating series. And an alternating series converges by the alternating series. This particular alternating series converges by the alternating series test. And that is all you need to say. You don't need to actually prove the alternating series test. In this case, you really don't need to say anything because that is an alternating harmonic series. That is one that you should, at this point, be pretty familiar with. Now we're going to go in and we're going to see what happens when we plug in 3 to our series. So we're going to have 3 minus 5 to the n, and that's going to change things a bit. Okay, now we go in and we check the other endpoint, and we see that that one actually turns into the harmonic series. And the harmonic series diverges by the p-series test. Now we're going to talk about something I had some questions on. I can't remember who asked these questions, but that right there will always, always, always be negative. It's telling you 2n plus 1, so that means that it's always going to be odd. That power is always going to be odd, which makes that number always, sorry, I shouldn't talk about things using pronouns. That number right there is always, always, always going to be -1, no matter what. I can't make it. Look at that. It won't point to the right thing. Okay, anyway, there we go. So when we actually write our interval of convergence, we do not include the number 3, but we do include the number 7 in our inequality. So we have found the radius of convergence, and we have found the interval of convergence. And I am so sorry this is so long. This is terrible. Okay, on this one, when we go ahead and we do the next term divided by the current term, we have to dividing fractions, y, square, just flip the last and multiply. And then we end up with this crazy looking thing, and the limit of 1 over a variable, it doesn't matter what the variable is, and in this case, it's a multiplication of 2 variables, that limit is going to be 0. So we have x squared times 0, and 0 is necessarily less than 1. Therefore, we have no more work to do, and we know that the interval converges for all real numbers. So the interval converges for all real numbers, and the interval of convergence is negative infinity to infinity, and the radius of convergence is, in fact, infinity. Okay, last problem. Okay, on this one, when we do the next term divided by the previous term, we end up with something that is linear, and the limit as n approaches infinity is actually infinity. And I made a mistake on the last one, and hopefully you guys caught it all the way up right under the letter B. I forgot to write n approaches infinity. Double check all notation whenever you take the AP exam or an exam in college, because you will get dinged brutally for those kinds of really stupid mistakes. I mean, stupid, like, I don't know, that's the wrong word. Really careless mistakes. Okay, so what we see here in this last one is that the radius of convergence is 0, and your series only converges at x equals 3. Okay, so we need to talk about something very quickly. A lot of you seem to think that you have handed in homework and it's not showing up on my end. So I actually emailed your parents, and according to your parents, you think you've done it, but it's not showing up on my end, so we have a little problemo. So what you need to do is you need to set up a Zoom call with me, because I don't need to see you personally. I need to see your screen, and I need to see that our blend pages don't match. So if you look in this picture, this is how I teach, with my cat behind me, just like that. I miss you guys terribly, terribly. I cannot tell you how much I miss you. I miss you so much. And I'm so sad about your graduation, but whenever you do graduate, I will be there because I miss you. And I can't wait to see you on Zoom, and I hope you're making the best of this time. And y'all take care.